Today we are going to solve a very simple problem that we have been looking in various methods, the Poisson equation, but we are going to use Rayleigh-Ritz method, a variational method, to solve such a problem. So let's look into the problem geometry itself. So we are going to have a square, so the square is going to be minus 1 to plus 1 and in both direction, in x and y direction. So if this is the x direction, this is the y direction. So if this is going to be the x axis, this is going to be the y axis. So this is going to be our problem geometry, and we are going to solve the Poisson equation. So this is going to be del square phi is equal to minus rho naught, and for the problem we are going to consider rho naught is equal to constant. So this is going to be constant across the entire domain, and we are going to solve this problem subjected to some boundary conditions. The boundary condition is phi of x comma plus or minus 1 is equal to phi of plus or minus 1 comma y is equal to 0. So that means for all x but plus or minus 1 y, we are going to have 0. So the potential is going to be 0 here, potential is going to be 0 here. Similarly for all y, for x equal to minus 1 and x equal to plus 1, it is also going to be 0. So along the boundary the potential value is going to be 0. So phi equal to 0, phi equal to 0, phi equal to 0 and phi equal to 0. So this is the problem definition, and let's go and look at how one can solve this problem using a simple technique of Rayleigh-Ritz. So we are going to take the problem from its symmetry. So if you look at this problem, there is a kind of a symmetry. So it's having x and y symmetry. So we are going to use a basis function based on the symmetry. So the solution to this problem will be of the form, so we have a Laplacian equation and we have said this is equal to constant. The general solution to this thing will be of the form where we are searching for an approximate solution, which is phi tilde. It is going to be of the form sigma n equal to 1 to n a of n u of n plus u naught. So this is going to be the general form, and of course depending on the number of basis functions this is going to increase in terms. So what we will have finally is of the form matrix equation, which will have the inner product of L of u1 comma u1 and the last term on the first row will be L of u1 comma un. Similarly here first term of the last row will be L of un comma u1. The last term here would be L of un comma un. So this will be the first on the left hand side multiplied by the basis functions that multiplied by the coefficients which are going to be a1 until an, and on the right hand side it is going to be a vector of g1 comma u1, inner product of g1 comma u1. The last term is going to be gn comma un, the inner product. So this is nothing but in the matrix form Ax equal to b, and we are interested in finding the value of x by taking the inverse. So this is going to be the way we are going to do this problem. What we are interested is in finding these coefficients. So that's the way we are going to solve it, and we'll see what the coefficients are going to be in the following steps. So since the problem is symmetrical, we can set the basis function we are going to use is going to be equal to u of mn is equal to 1 minus x square multiplied by 1 minus y square multiplied by x power 2m y power 2n plus x power 2n y power 2m. So for m comma n equal to 0, 1, 2, so on and so forth. So this is going to be the basis function we are going to use. So let us say we have the problem using this basis function. So what we will get is, we will get the solution itself as an approximation. So the approximate solution is going to be phi tilde is equal to of the form 1 minus x square multiplied by 1 minus y square multiplied by a1 plus a2 multiplied by x square plus y square plus a3 x square y square plus a4 x power 4 plus y power 4 plus so on and so forth. So let us take a very simple case where m is equal to n is equal to 0, the first case. So the case 1 is equal to, the number of basis function is going to be 1. So that means m is equal to n is equal to 0. So if we have that, let us club this into this equation. What we get is u of 0 comma 0 is equal to 1 minus x square multiplied by 1 minus y square, and putting m equal to n equal to 0, what you will get is this value will become 1 and this value will become 1 plus this value will become 1 multiplied by this value will become 1. So the entire thing will become 2 times 1 minus x square multiplied by 1 minus y square. So this will be our basis function. Once we do that, we can multiply this into our equation in a clever way by taking the inner product. So we will have the first coefficient, which is given by L of u1 comma u1. Remember, the inner product is defined as u v dv. If we say this is the inner product of u comma v, so in this case it is going to be a double integral for minus 1 to 1, minus 1 to 1 for x and y, and the L operator in our case is equal to the Laplacian operator. So we can say the Laplacian operator is going to be dou square by dou x square plus dou square by dou y square. So we are going to write the Laplacian operator here. And we are going to multiply it with u1, put this into a bracket, and you have u1 which is going to come. Remember, this is the way we define the inner product, and multiplied by dx dy. So this is going to be the first step, and the next step is I am going to introduce u1, and we have found the value of u1 in our previous step, which is going to be 2 multiplied by 1 minus x square multiplied by 1 minus y square. And I am going to differentiate this twice with respect to x and add it with the result I get after differentiating twice with respect to y square and multiply it with u of 1, and this is going to be again multiplied by dx dy, and that is what I am going to do exactly now. There is some level of symmetry in the problem, and the symmetry is here very clear that it goes from minus 1 to 1, minus 1 to 1 on both sides. So I can take 0 to 1, 0 to 1 and multiply it by 2 twice. So that is what I am going to do here. So I am going to write it in a simplified form. A11 is equal to minus 8 integral 0 to 1, integral 0 to 1. I am taken half of the integral and I am going to multiply it with 2, and I am going to do that also for x and y. So the outside multiplier will be minus 8, and the result of differentiating with respect to x twice and adding it with the differentiation with respect to y twice and multiplying it with u1 will lead to this form. So 2 minus x square minus y square multiplied by u1, which is 1 minus x square 1 minus y square dx dy. So this is going to be the first thing, and we will see in the MATLAB code how we can reduce it and get the value for A11. So this is going to be the first one. The second one will be the right hand side. So what we will get on the right hand side will be, so this is the first coefficient that we are computing, A11, and we will also have the first term on the right hand side. So remember, this is, if you are using a 1 basis function, the matrix of Ax equal to B will have only A11 term, and the x term is going to be A1 is equal to B, which is nothing but G1 comma U1. Since G is constant here, so G is nothing but the value of rho itself, rho naught. So it is a constant, we are putting as G, not G1, G2, G3. So here A11 is the first term and the only term that we have, and we are interested in computing the right hand side term, which is B term. For B1 we write it B1 because we are in the first case with only one basis function, n equal to 1 is equal to inner product of G comma U1. So this is going to be written as minus, because G is minus rho naught. In fact, I forgot the minus sign, so you have to put a minus sign here. That is how we have defined the problem initially. So the problem definition is the Poisson equation, and the Poisson equation has a minus sign here. So that minus sign should be the value of G here. So minus sign comes out, minus 1 to 1, minus 1 to 1, 1 comma x square, 1 minus x square, 1 minus y square, rho naught dx dy. And when we simplify this, what we get, and when we simplify this and apply the value of x and y, what we get is B1 is equal to a value that we will compute in the program, and we can also do it numerically by hand, but we are going to do it in a MATLAB code, and I will show you how to do this. So this is going to be for the first approximation. So now let us look at, if I increase the value of n equal to 2 and n equal to 3, n equal to 4, so on and so forth. So if n is equal to 2, what you will have is 2 basis functions. So the phi tilde is equal to A1 U1 plus A2 U2, and you will compute the value of U2 from the general equation of U of m comma n, which we described it as 1 minus x square 1 minus y square multiplied by x to m y to n plus x to n y to m. So you are substituting the value for m equal to n equal to 1, and for the second case, and m equal to n equal to 0 for u1, and this is for u2. So this is what we are going to do, and we will get accordingly the different values for u1 and u2, and based on that we are going to compute not just one term but a series of terms. The series of term will be A11, A12, so A11 and A22, sorry, A11 and A22, and here A12 and A21. So this is the size of the matrix for n equal to 2. The size of the matrix will increase for n equal to higher numbers by having more and more terms on the matrix, and there is going to be some symmetry between the elements. So A12 and A21 should be same. So A12 should be equal to A21, whereas the diagonal elements are going to be unique, and that is what we are going to see in the MATLAB code. So now let us go and see the MATLAB code itself. So this is going to be the MATLAB code that we are going to use. We are going to use the MATLAB code for solving Poisson equation using Rayleigh-Ritz method, and we are going to use a specific toolbox which is called as symbolic toolbox. Some MATLAB versions do not have the symbolic toolbox. If you do not have it, you have to install it. It is very easy and elegant to do it with the symbolic toolbox, that is why we are showing this. And for simple problems you can also do it differently, but symbolic toolbox will be a very elegant thing because we wanted to see the expressions as well. So for the first case we are going to put n equal to 1. If we put n equal to 1 and we are going to initialize the derivative matrix, so the first derivative matrix, the second derivative matrix, because we need them in our definitions, in our expressions. So if you see this part, we are going to have both the derivatives. So we have to compute the second derivative, and in order to compute the second derivative we have to compute the first derivative, and that is what we are doing here. So our goal is uxx and uyy, but to get uxx you have to derive ux, and in order to derive uyy you have to get uy, and you are initializing some of the intermediate matrices, and the coefficient matrix is going to be C and the solution matrix is going to be phi. Initially you set solution to be 0, so this is the way we start doing the problem, and while we simulate the problem and get the solution will be different. So initially we set it to 0. So we are forming the matrices, and the matrices are formed based on the equation we have 1 minus x square 1 minus y square, x power 2m y power 2I, and we are using I instead of n here because we are using n for a different variable. So we are using I instead of n. So wherever there is I you have to substitute it in the derivation which we showed before as n, and once you do that you do the derivation of it using inbuilt function called diff. So this is a MATLAB function which allows you to do that, and you are computing the inner products on the left hand side and you are computing the inner products on the right hand side as follows. And once you do that you do the matrix inversion to compute the value of C, and you compute the solution for the domain. So this is a very straightforward, and we are going to print the solution in the final step. So now we are going to do this for n equal to 1. So let us run it, and let us go back to the code itself here, and what you see is we get 5 by 32 as a value, and the potential itself is going to have this function. So what it means is the phi value is going to depend on the value that we are going to compute. Here 5 by 32 is the coefficient that we have, which is coming here as 5 by 16, because do not forget the value that we have chosen for u1 is going to be, so let me explain this. So the coefficient is a11 multiplied by the value of u that we are having. So here the value of a11 is going to be 5 by 32, and u1 is going to be the value that we have, which is 2 multiplied by 1 minus x square 1 minus y square. So 2 and 32 goes away, it becomes 5 by 16, and if we swap it to x square minus 1 there will be a minus sign, and this minus sign goes here, and then we swap it one more time, it gets cancelled. So we will get 5 by 16 x square minus 1 y square minus 1. So that is what is the solution what you get on the MATLAB program here, 5 by 16 x square minus 1 y square minus 1. So now let us go and do it for n equal to 2. So for n equal to 2 you will have 4 values, in the matrix of A. So we are going to run it. So you will see that there are 4 values. The first value is the same value that we had before, 5 by 32, which is good, and we are getting another value which is 147 divided by 352, and as I explained before, A12 which is 105 divided by 352 is the same as A21 which is also 105 by 352. In other words, I write it again, A11, A22, A12 and A21. This is going to be the matrix, and we are getting A11 in the first case and also in the second case as 5 by 32. We are getting A22 as 147 divided by 352, and we are getting A12 is equal to A21 is equal to 105 divided by 352, and this is what we are seeing in the matrix here, in the C matrix, in the equation. And as we had before, we are going to have one term because of this element, one term because of this element, and one term because of this element, because it is getting repeated, so it will get added up. So we will have totally 3 terms. So this is the first term, this is the second term. So until here is the second term. So this is the first term, and this is the second term, and you have the third term which is going to be from here until the end of the equation. So this is the third term, and the numerators have to be same as here, and the denominator will be divided by 2 because there is a numerator 2 that comes from UN definition itself. So anyway, so this is the way we have computed it for n equal to 2, and you can go in higher orders. The beauty of doing it with the symbolic toolbox is it allows you to have different orders. So for example, if you have n equal to 5, you simulate the program, what you will get is 5 terms on the leading axis for C, so one term here, one term here, one term here, one term here, and one term here. So these are the 5 terms. First, this is the last term, and this is one term above, this is the third term, and this is the fourth term, and this is the fifth term. So these are the leading diagonal terms, and you can see 5 by 32, 105 by 32, 105 by 352, and those terms are repeating, and that is how it should repeat because we are going higher in number of basis function, whereas the lower basis function values will get repeated. So what we have done in this problem is we have simulated standard Poisson equation using a very useful toolbox called as symbolic toolbox from MATLAB, and we have simulated it for very many basis functions. The reason for going for symbolic toolbox is to allow you to create a general program, and you can do it for different number of basis functions, and we have showed that for this case. Please take the code and try it for yourself, and as I said before, you need a specific toolbox which is a symbolic toolbox, which is something you can download for MATLAB, and try it out for yourself how one can use the inbuilt functionalities cleverly to solve such simple problems. Thank you.